In the earlier lecture, we have seen the definition and properties of Brownian motion, and today we are going to see some more results of Brownian motion. We are going to see first definition of Itoâ process. Itoâ process is a stochastic process which is written in terms of Brownian motion and some other appropriate processes. So, let us see that definition. Let W be a d-dimensional Brownian motion. Here Brownian motion is denoted by the letter W. This W stands for the initial of the mathematician Wiener. So, this W we take on the probability space omega f p, and we assume that this W is adapted to the filtration f t. N-dimensional Itoâ process is of the form x t is equal to x naught plus integration 0 to t u of s ds plus integration 0 to t v of s dws. Here u and v are function of time and omega. Omega is actually the sample points. So, that means these are random variables. However, it also depends on s is time. So, this is time dependent random variables, or in other words u and v both are stochastic processes. So, we are integrating here the stochastic process u with respect to time, and here we are integrating the stochastic process v with respect to the Brownian motion w from 0 to t. And then the integration what we obtain at the end, and that if we vary over time we get a stochastic process. So, that process is going to call Itoâ process. Okay. So, Itoâ process is a class of processes, correct. So, this is a large class of processes which can be written in this manner, that the process x t can be written as sum of these three terms. One is x naught, where x naught is f 0 measurable finite valued random variable, and then we have integration of a stochastic process u which is f t adapted, and the probability that integration of mod u ds is finite with probability 1. And then v is also there, where this integration of v with respect to Brownian motion is taken. Then we call this and v should be integrable with this Brownian motion. So, we choose v to be a member from that script p of w. So, this class of processes we have already discussed when we have developed the theory of integration. So, these are the conditions on u and v. If we can write down a given stochastic process in this manner, where u and v are satisfying these conditions, then we would call this stochastic process as an Itoâ process. Okay. So, remember the this adaptiveness is very important here. U and v both are adapted to the same filtration where Brownian motion is also adapted to. Next, we see one formula which is consequence of Itoâ's formula. So, here we start with process y. So, y be an Itoâ process of the form y t is equal to x plus integration 0 to t u ds plus integration 0 to t v dws. Okay. So, we are suppressing here the dependence of u and v on omega, because that is the thing we do generally, but in the earlier slide I have written explicitly the dependence of u and v on omega to emphasize that u and v are allowed to be random variables, okay, allowed to be stochastic processes. Now, we consider a function f which is twice continuously differentiable and has compact support. Okay. So, compact support functions and continuous and compact support functions are bounded, and its all derivatives are also bounded, the much of derivatives it can possess. So, and tau we consider an ft stopping time with finite expectation. Assume that if tau is the time of exiting the support of f. What is support of f? It is a compact subset of Rn, correct. Here we have considered f is a function from Rn to R, real valued function on Rn with compact support. So, now if you count the time when yt, this process which is coming from here, hits the boundary of the support and goes beyond the support of f for the first time, and you call that tau, then tau becomes a stopping time, ft measurable ft stopping time. Why? Because yt is coming from here, and then u, v and w all are ft adapted processes. So, in return we get yt is also ft adapted. We are just counting the hitting time of the boundary of the support of f by the process yt, which is ft adapted. So, tau also becomes a stopping time, ft stopping time, correct, with respect to the stopping time ft. Now, if we assume a further condition on u and v, namely that given the stopping time, the stopped process of u and v, that is u t minimum tau and v t minimum tau, they are also bounded. So, this is an additional condition on u and v. So, we assume this additional condition for this following result. So, under this assumption, we can obtain the following result, that expectation of f evaluated at yt, okay. So, f of y of tau, sorry, not t, y of tau is equal to f of x plus expectation of integration 0 to tau us dot, this is dot product, this is gradient of f. So, this is derivative of f, correct, in multidimensional. So, f is from Rn to R. So, the total derivative of f is also function from Rn to R, okay. So, of ys, and then we are taking this is a vector, u is a vector, and we are taking dot product of u and the derivative of f plus half times summation over ij v is v star is v, here star stands for transpose v star. So, v is a matrix here, correct, because w is Rn value stochastic process and v is a matrix here, matrix valued stochastic process. So, v star is also a matrix, and we are considering ij component of v star, and then we multiply that with the second derivative of f with respect to I and j. So, del 2f del xi del xj evaluated at ys and ds, and then s is, we are integrating with respect to s from 0 to tau. So, we would prove this result. So, before proving the result, let us again revisit the terms more carefully. Here we have only two terms. One term is involves the first derivative of f, and second term involves second derivative of f with half term. So, we can figure out that okay, this is the term which appears in the Ito's formula for the which is attached to the quadratic variation process of Brownian motion, and we have seen the quadratic variation of the Brownian motion is time itself identity. So, that ds is coming, okay, and this first order term, okay, first order derivative term comes with the dyt term, but dyt term is here us ds plus this thing, okay, plus the local martingale part, and this us is appearing here, ds is appearing here. So, we can understand that basically if you write down Ito's formula for function f and the process y, and then you are going to get without expectation the terms, these terms, and one more additional term. What is that? That is gradient of f, and then the matrix v and dw. So, this term should appear, but that is absent here. So, only reason that to be absent is that possibly the expectation of that is 0. In view of Ito's rule, it is sufficient to prove that the expectation of integration this v del f del x dw is 0. Okay. So, this is the thing we need to prove. Okay. Earlier I had this summation that I took out of the expectation. So, let us see the indices more carefully. So, V is a matrix V I j, ijth entry of V matrix, and then del f del x I. Okay. So, ith component of the derivative of f, and then jth component of the Brownian motion. Okay. So, if you write down as a in terms of matrix notation, then del f del x would come as a vector, gradient of f would be on the left hand side. In between you would have the matrix and then the Brownian motion, and possibly left hand side the del f del x you would write down as a transpose of that. So, that it is like a row vector. Okay. So, that you are going to get a scalar out of it. Okay. So, this whole thing is a scalar, correct. So, this is a scalar 0. So, we need to prove that this is 0. So, that is the goal. So, if we do that, then nothing more is required, then this is immediate. Okay. So, in view of Ito's formula, we just need to prove this expression is 0. Okay. Note that the integrand is bounded process here. Why? Because of the assumptions we have made, that tau is the time. Okay. So, within the time tau, u and v behaves like a bounded process. Okay. And the integration will be for 0 to tau. So, there u and v are all bounded. Okay. And function f is twice quantitative differentiable function on the compact support. So, the function and its derivatives all are bounded. So, this part is bounded, this is bounded. So, integrand is bounded. Okay. So, now we have an integration of a bounded process with respect to Brownian motion. Okay. And we are now trying to minimize our notations. Okay. So, instead of writing all the details, we are going to write down just G. Okay. So, it is sufficient to prove this type of identity for some G, okay, where G is a bounded adapted process. So, that is a property of these functions. Okay. So, just a general G. Actually, this is true, this is 0 for a general G. So, we are going to prove that. Okay. So, let us assume that G is a bounded process with an upper bound capital M. Okay. G s is less than or equals to M, mod of G s is less than or equals to M for all this. So, now for all integer k, we have expectation of 0 to tau minimum k. Why are we doing tau minimum k? Because tau itself need not be a bounded random variable, correct. However, if we put a minimum with k, that means we put a bound on that. So, then this tau minimum k remains another stopping time, but bounded stopping time. Okay. And if it is bounded, then we can actually argue better. So, we consider some integer k, okay, positive integer k, and take expectation of 0 to tau minimum k g s dws. Then this integration can be rewritten as integration 0 to k, and then indicator function of 0 to tau of s. Okay. If s is equal to or more than tau, then this part would be 0. Okay. So, when we integrate with the Brownian motion from s to s is 0 to k, then for occasions where tau was below k, there this part would become 0 after tau onward. So, this integrand would not contribute anything. On the other hand, if tau is more than k, this part would be always 1 all the time during 0 to k, and therefore, I would get this integration from 0 to k. So, this is always a finite interval integration g s dws. And here we see that okay, G this is bounded, the whole thing is bounded, f is measurable. Okay. So, when we have bounded f is measurable process, we know that it is in the class of LW. Okay. LW is the space of processes which are adapted and it is square integrable. Okay, so those conditions are satisfied. So this is going to be a square integrable martingale. Okay, since it is a martingale, okay, so when 0 to t is there, okay, like as a function of t, now it is 0 to k. Okay, so that means the martingale evaluated at time k. Okay, so expectation of that would be 0. So we get that this is 0, but we get this is 0 for the modified stopping time, that is truncated tau minimum k. Okay, but this is true for all possible k. Okay, so that is the thing we are going to use next, that we actually need to discuss about this integration, but we have obtained result about this integration, which is integration gs dws 0 to tau minimum k. Now we are looking at the L2 distance between these two random variables. Okay, expectation of square of the difference. Now we see that that is equal to this difference is 0 to tau and 0 to tau minus k, that means tau minimum k to tau. Okay, this integration of g square. So here we are applying the Ito's isometry formula, correct. So then we are getting that expectation of this g square ds. Okay, less than or equal to. So Ito's isometry formula involves, the first version involves only the deterministic time both the sides, but then for general stopping times also we know that we have the same Ito's isometry formula. So we are using that here, and here we have g square, but g is a bounded process, upper bound m. So g square can be upper bounded by m square, and then it is integration of this time. Okay, so this difference is tau minus tau minimum of k. Okay, expectation of that. However, tau is assumed to have finite expectation. Since this has finite expectation, okay, so tau minimum minus tau minimum k, that would go to 0 as k tends to infinity. Why is it so? Because anyway as k tends to infinity, this converges to tau almost surely. Okay, as tau is finite valued, so this converges almost surely, but that tau is having finite expectation. So we can actually use dominated convergence theorem, that this difference is dominated by 2 times of tau, which has finite expectation. So we can actually take limit inside, and the expectation of this thing goes to 0 as k. Okay, finite expectation of tau is used here. Therefore, integration 0 to tau minimum k g s dws, this thing converges to this in L2, because we got it correct. So this L2 norm distance goes to 0, converges to L2. So L2 convergence also implies L1 convergence for probability measure. So we get that this expectation is 0 all the time. So this is 0 all the time. So for limit also it is 0. However, this limit is same as expectation of 0 to tau gs dws, since they converge in L1. So at the end, what we have obtained, that 0 is equal to expectation of integration 0 to tau gs dws. So this is the end of the proof.